Okay, and now I've hit the go live, so we should be good. All right, so let's get started here. I am Terry Camerzell, and I'm here on behalf of Creation Fellowship Santee. We're a group of friends bound by our common agreement that the creation account as told in Genesis is a true depiction of how God created the earth and all life in just 6 days about 6,000 years ago. We used to meet in person at the Creation and Earth History Museum in Santee, California, but took to this online platform in June of 2020 and haven't looked back. God has blessed us with presentations by many talented people who love the Lord and have a message to share. You can now find links to most of our past presentations by typing in tinyurl.com/C like creation, F like fellowship, and Santee is spelled S-A-N-T-E-E. You can also email us at creationfellowship@gmail.com to get on our email list so you don't miss any upcoming speakers and we never spam. Tonight, we're excited to welcome back our friend and fan favorite, Dr. Jason Lisle. Dr. Lisle is an astrophysicist and founder of the Biblical Science Institute. As a perpetual student of the Word of God, he also teaches and writes on other topics such as the hermeneutics of Genesis, the mathematic patterns of nature, general creation apologetics, and now homeschool students and adults alike are learning more and more to pattern their thinking after the mind of God thanks to Dr. Lisle's Introduction to Logic curriculum. But tonight we invite you to put on your thinking caps and pull out your air microscopes as we travel from the vast knowledge of God and the great expanse of the heavens down to explore the tiniest theoretical constructs we believe to exist, quantum particles. If you have questions, if you're watching on Facebook or if you're in Zoom and you have questions for Dr. Lisle that you'd like us to ask him after his presentation during the live Q&A, you can post them into the chat on Zoom or into the comments on Facebook, and we'll keep an eye on those and ask him those. So with that, Dr. Lisle, it's your turn.
Okay, well, it's good to be with you this evening virtually and talk about quantum particles. The quantum physics is the branch of physics that deals with the very, very small and how the universe behaves at the smallest scale, smaller than atoms. And I think I guess I'm attracted to the extremes of physics. I like the universe because it's as big as you can get physically, and then quantum is as small as you can get in terms of structure. The rest is just filler. So I I like the extremes, I guess. And although I didn't end up specializing in quantum when I got my PhD in astrophysics, it's something that I find very interesting. And I hope that my enjoyment and interest in the topic will be appreciated. I hope that you'll find it enjoyable as well. Because the field is so vast in terms of the information, quantum mechanics is a wonderful, interesting field, but it's difficult. And that's because many of the aspects of quantum particles are counterintuitive. And so I'm going to, of necessity, have to limit the topic tonight. And I'm just going to limit it to really elementary particles and some of the ways that they combine. An elementary particle is a particle that is not made of anything smaller. Hopefully, anyone I think who's graduated from high school would know that we're made of molecules, and then molecules are made of atoms. Atoms are made of electrons circling around the exterior, and then the nucleus, you got protons and neutrons. And so atoms are composite particles because they're made of something smaller. But there are particles that the Lord created that, as far as we can tell, are not made of anything smaller. And so those are the particles that I'm going to discuss this evening. And I'll give you just enough of the background of quantum mechanics that you need to know to be able to understand these particles. Obviously, there's a lot more that I could cover, but I rehearsed this a couple times and went far longer than you will want to listen to me. So, and I have some illustrations too, I think that will make this a little more tractable. So here we have an illustration. This is a schematic of a helium atom. So you have the electrons, there's two in a helium atom if it's neutral, and they're orbiting around the nucleus. This is not to scale. The nucleus actually would be invisible at this scale. It's very tiny compared to the size of the atom. And then the protons and neutrons in the nucleus of that atom are also composite. They're made of smaller particles called quarks. And so our goal this evening is to introduce you to the elementary particles that are known or suspected to exist. There are only 38 And these are the elementary particles that we know to exist, and one has not yet been experimentally detected. But yeah, so that's it. And already you can see that they're not random. They're organized into, I can organize them into this chart because they fall into natural sort of families and families of families. And that's one of the takeaways that I want you to get from this presentation, is that the particles that God created and allows to exist, and they can transform into other particles, but it's always these 38. These are the 38 particles that, as far as we know, are made of nothing smaller. Already you can see that they're divided into two broad families, bosons and fermions. You can see that at the top there, just under elementary particles. Those are the two major families. Within the family of fermions, there are 2 or 4 families, depending on how you look at it. You have leptons and quarks, and then you have antileptons and antiquarks. And then under the bosons, there are sort of 5 families of bosons, 4 of which are connected to fundamental forces. And then there's the Higgs boson, and it's just weird. It's kind of an outlier. It's there, but nonetheless, these particles exist, and the way they exist makes life possible, and it shows something about the creativity of God. Obviously, the particles don't look like this. This is just a schematic to help us kind of remember it. And I use colors to indicate things like electric charge. Just kind of gives us something visual. I'm a visual learner, so hopefully that's helpful to you as well. And so there are 3 takeaways that I want you to get tonight, because as we study these particles, the details, they're fascinating, but it gets complicated. And so I don't want you to get lost in the details. There are 3 takeaways that if at any point you say, I didn't quite follow that, make sure you get these 3 takeaways. First of all, elementary particles exist in a nested hierarchy. A nested hierarchy means there's an orderliness to it. It's like a family tree, but it's a nested hierarchy. You can have families within families. And that's significant because in the world of biology, you can also do that. Taxonomy, that's all about classifying organisms, and we find that they occur in a nested hierarchy, which is why we can have, kingdom, phylum, class, order, family, genus, species, and you can have organisms that are in the same family, but they're, different genus and so on. You can do that with quantum particles too. And I find that interesting because secularists, evolutionists, like to say that the nested hierarchy we see in the world of biology is due to evolution. And that's the only explanation for it, is the reason we can organize organisms into similarities and differences, families of families, is because they have evolved from a common ancestor through gradual changes over millions of years of reproduction. You can't do that with particles because there are only 38 elementary particles. That's it. And they don't evolve. Electrons do not gradually, they don't reproduce and then gradually gain weight until they eventually become a muon. Particles, unlike animals, can decay. They can change into other particles instantly, but it's always some combination of the 38 particles that exist. Everything in the physical universe is made of those 38 particles, or some combination thereof. So that is a powerful demonstration that the evolutionists are wrong, that a nested hierarchy can only be explained by evolution. You can't do that with particles. Secondly, the properties of these particles are highly mathematical in nature. Some of these particles were predicted to exist on the basis of math before they were discovered. I think that's wild. You can't do that in biology. Nobody predicted the existence of an elephant based on some equation, but there are particles that were predicted to exist on the basis of a solution to an equation that were subsequently discovered empirically, experimentally, and confirmed. I think that's amazing. The positron was predicted to exist before it was discovered. The top quark was predicted to exist on the basis of math. And secularists can't really explain why the universe obeys math at all. And it gets particularly sticky when we deal with quantum particles that are so highly mathematical, we can actually predict, in many cases, which kinds exist. That's pretty neat. And that makes sense in a Christian worldview because God's mind upholds the universe and God thinks mathematically. That's why math applies to the physical universe. And then third, the properties of these particles are exactly right for chemistry and biology, for chemistry to be what it is, and therefore biology for that to be possible. I'm not big on fine-tuning arguments. There's nothing wrong with them. I just tend not to use them because normally it's hard to say what the range is. Like the Earth is the right distance from the sun for life. That's true. But how precise is it? If we move the Earth 5% closer, could life still survive? If we move it 10% further away, could life still survive? that's hard to estimate because weather, climate, it's complex, and the robustness of life is complex. But with particles, because quantum particles obey these math equations perfectly, we can tell what they would be like if they were a little bit different. If you made the up quark a little bit more massive, we can tell what it would do. And we know that in many instances, life wouldn't be possible if these things were just a little bit different from the way they are. And so it really gives you a glimpse into the magnificence of the mind of God to think of all these interactions in such a way that makes the universe the way he wants it to be. It's remarkable. So those are the takeaways. And so let's get into some of the details. I guess one of the things that I need to start with is the properties of quantum particles. They often have mass. We have a feel for that. We understand mass. You know, if you're more massive, you weigh more on the scale and so on. Quantum particles can have mass, although some of them do not have mass. There are massless quantum particles where if you were to stop them, they would weigh nothing, like particles of light. Photons have no rest mass. And there are other particles that likewise have no rest mass. Some of them, however, are very massive. So that's one of the properties of quantum particles. Another is charge. They can have electric charge. Like the electron has a negative electric charge. The proton has a positive charge, although proton is composite. It's made of particles that have charge, and so on. So those are some of the properties. Those ones we kind of have some familiarity with, because if you've ever played with magnets, you know something about, you know, north attracts south and so on. And that's an aspect of the electromagnetic field. Particles can also have a thing called spin. And one of the neat things about quantum is a lot of the terminology we use are very basic English words. I really like that. It's not like in biology where everything's Latin. If you know English, you can talk about quantum mechanics. Particles have spin, which means, yeah, they can rotate, they can spin. And that should be obvious with things like molecules. Think of a water molecule. It's got the big oxygen there and the two hydrogens. I can hit that thing on the right side and sure enough, it'll spin because it has size to it. And so it can rotate. But one of the things that's interesting about quantum particles is that many properties of these particles are quantized. That's where we get the word quantum. And that basically means they come in certain discrete levels, but nothing in between. And that is caused by the wave nature of matter. And I don't want to get into too many details of this, but the reason that electrons, for example, can only orbit in certain shells around an atom and not in between is because of their wave nature. So electron acts kind of like a wave at times with peaks and troughs. And the distances where it can orbit are distances where the circumference is an integer number of wavelengths. So when the electron comes back, so the electron is like, say, a peak when it's here. When it comes back around, it's a peak again. That works. If you made the orbit different, where the peak, when it comes around the next time, would be a trough, they would cancel out. And so the electron could not exist. That's why orbits are quantized. And a lot of properties of quantum particles are quantized, including spin. So it's true, I can spin that water molecule. I can give it a little more energy. It'll spin a little bit more, but we'll find that it's quantized in that a water molecule can spin at a rate of 3 rotations per unit time, or 2 or 1 or 0. I can stop it, but it can't orbit at 1/2. It can't rotate at 1/2 or 3/2 or anything like that. Spin is quantized. And so it's quantized into these integer units. And it turns out that quantum particles also have spin. And let's see if I have a little illustration of this. So here we have electrons, for example. These are supposed to be electrons, and a depiction of them. And they can rotate. And we talk about the direction of their rotation using the right hand rule. So if they're spinning, if you take your right hand and curl your fingers in the way that the particle is spinning, the direction of your thumb is the direction of the spin. So spin up would be a particle like you see on the left there, and then the right is spin down and so on. So molecules can spin that way. Elementary particles that are not made of anything smaller, can spin. And this is weird for 4 reasons. First of all, as far as we can tell, elementary particles have no size. Every experiment that's tried to detect size to these particles, I've depicted them as little spheres, but technically they're points. But of course, I can't depict a point because it has no size. How can something that has no size rotate? I mean, a sphere, yeah, you push on this side and you pull on that side, it rotates because it has sides. A point doesn't have sides, it's just a point. And so how can it rotate? Well, it really can't. It's best to think about these elementary particles as having something that is mathematically like rotation. They have a little bit of built-in angular momentum, despite the fact that they don't have any size. So that's one weird aspect of these quantum particles. And all elementary particles have spin associated with them, except the Higgs boson. It does not spin. The second weird thing is that with a molecule, I can speed up or slow down the spin by giving it energy or removing energy. And now it's quantized. I can, increase it from 2 to 3 to 4 to 5. I can't go in between. But with elementary particles, they are born spinning, and you cannot change the amount of spin. For example, a photon, a particle of light, has a spin of 1, and you cannot change that. That you can't make it 0, you can't make it 2. All photons have a spin of 1. They're born spinning, as so to speak, and there's nothing that can change that. That's kind of weird. The amount of spin cannot be changed. The direction can. If you have a photon that's spin up, because it's spinning this way, there are conditions where I can rotate it and make it spin down. That we can do, but the amount of the spin cannot be changed. It's apparently set by God and is built into particles, and it affects their behavior. So we can redirect the spin. We can change a particle from spin up to spin down, but we can't affect the amount of spin. The third weird property of spin is when we talk about the direction of the spin, it's quantized in that when we measure the spin state of a particle, like an electron, the two that you see there, it will either be spin up or spin down. You might think of it as, what can it be this way? Not when you measure it. Whenever you measure it, it'll either be aligned with your detector, spin up, or anti-aligned, spin down. What if I rotate the detector at a 45-degree angle? Then it'll be spin up or spin down. That's just part of the weirdness of quantum mechanics. And then the fourth thing that's really strange is that many elementary particles are born with a spin that is impossible for us to achieve, in that it's a half integer. Electrons, for example, have a spin that is a half. Now, we can't get a molecule to go to a half. A molecule can be 1 or 2 or 3 or 0. We can't get it to be a half. And yet many of the particles that God created are born spinning at a rate that is impossible, because it's halfway in between two integers. So particles in the quantum world can have a spin of a half or 3 halves or 5 halves, or they can have a spin that's an integer. And that's weird, basically. At least I think it's weird. That's part of the weirdness of it. And based on the way these particles spin, whether it's an integer, which is kind of what we'd expect, or a half integer, which seems impossible, that will affect the behavior of the particles so much that that's the first division in terms of the family of these elementary particles. Elementary particles are divided into fermions or bosons. A fermion is a particle that has a half integer spin, 1 half, 3 halves, 5 halves, something that's exactly in between two integers. And as far as we know, spins can't be anything less than that. They can't be like a fourth or a third, but you can have half spins, but it's built into the particle. So that would be fermions. And then bosons are particles that have an integer spin, like particles of light. Photons are bosons, and so because they have a spin of 1. Electrons, which are fundamental elementary particles, they have a spin of 1 half. And that causes them to either obey or disobey a particular rule called the Pauli exclusion principle. Fermions obey it, bosons disobey it. The Pauli exclusion principle says that you can't have two identical particles in the same quantum state at the same time. What's a quantum state? The same place, same energy level, same spin state. Okay, and so if I have an electron here and it's spin up, and I try to put another electron in that same location, same energy level that's also spin up, nature will not allow it. It can't be done. And that is why the lowest energy shell in an atom contains 2 electrons and no more. You know how atoms have these shells of electrons. You can only put 2 in that bottom shell because one of them will be spin up, the other will be spin down. If I try to put a third in there, it'll either be spin up or spin down, and you'll have 2 that are both spin up or both spin down. That's forbidden by the Pauli exclusion principle. So that the Pauli exclusion principle, combined with the fact that electrons or fermions, is why all chemistry is possible. Because bosons do not obey that rule. Boson, you can put as many bosons in the same quantum state as you want. Photons, you can put as many photons in the same quantum state. That's what a laser is. A laser is multiple photons existing at kind of at the same place at the same time, the same energy level. And you can do that with light. You can't do that with electrons. So had God made the electron, had he given it a spin of 1 instead of a spin of 1/2, then electrons would be bosons. They would disobey the Pauli exclusion principle. And you could put as many electrons into that lowest energy level in an atom as you want, which means chemistry would be impossible. The periodic table would not exist. You can have multiple atoms, but they all would act chemically like hydrogen because all the electrons would drop into that lowest energy level. So it's just weird. This just because the electron spins at 1/2 rather than 1 or 0 is part of what makes chemistry possible, which I think is kind of amazing. So it's just one of the things that God thought about when he's creating this universe. So bosons do not obey that Pauli exclusion principle. In fact, they go out of their way to disobey it. They're just rebels. But so we're going to start with looking at the elementary fermions, and this will take the most time, especially when I get to quarks. So if we're still on quarks and you're like, oh my, he's taking way too long, the bosons will go really fast. So we're going to take the most time with these because there's some introductory material here that needs to be explained. So the elementary fermions contain 2 families, leptons and quarks, or if you will, 4, because there's anti-leptons and anti-quarks. And we're going to start with the leptons because they're easiest. And you already know one, the electron. The electron is the lightest charged lepton. The word lepton means light ones, not light like photons, but light in the sense of not heavy, very low mass. Leptons are very low mass, except for the tau. That's the one exception. And it wasn't discovered yet when they gave the name leptons. All the existing known leptons were light at that time. The electron, you can see on this table here, it has a mass that is, well, I gave 2 different units for the mass. I gave kilograms because that's something we're kind of familiar with. You might know your weight, a person might weigh 80 kilograms. I mean, it's your mass actually, but, and so the electron by comparison is 9.1 times 10 to the negative 31st power kilograms. So it's very low mass. And because these particles, all these quantum particles are low mass compared to the stuff we deal with every day, we tend to use different units. We tend to use MeV. MeV is million electron volts. That's actually a unit of energy. We divide by c squared to make it a unit of mass. And so electron is 0.5 MeV. That's pretty light for an elementary particle. Most particles are heavier than that. So you know about electrons. They are elementary as far as we know. You may not have known the electron has a big brother called a muon. A muon is identical in every way to an electron, except it's 200 times heavier. For whatever reason, it's just heavier than an electron. But all the other properties are the same. They all have a spin of 1/2. All leptons do. The 3 on the top row all have a charge of -1. So does the muon and the tau. The tau is an even bigger, heavier version, and it weighs 1.7 billion electron volts, which is quite heavy. Well, it's heavy for a lepton. In fact, that's about twice the mass of a proton. So there you go. The electron, on the other hand, is almost 2,000 times less massive than a proton. That's why the electrons zip around the outside of the atom and the proton just wiggles slightly because most of the mass is in the center of the atom. So electrons don't contribute very much to your mass. It's primarily the protons and neutrons that do. There are neutral versions of each of these 3 particles that you see on the top, and they're indicated on the bottom table. You have, and they're called neutrinos. Neutrino means little neutral one. There's a neutrino version of an electron neutrino, there's a muon neutrino, and there's a tau neutrino. So they're just neutral versions of the charged leptons that you see in the top. And one other difference is they're extremely low mass, less than 1 electron volt. Okay, an electron is 0.5 million electron volts. Neutrinos are less than 1 electron volt. For a long time, physicists thought they were completely massless, like photons. But we now know, because of the math that they obey, that they must have a small finite amount of mass, but we don't know exactly what it is. And so we just know that it's very small. The neat thing about neutrinos is they're kind of like the ghosts of particles because they can pass through ordinary matter. And in fact, right now, Every second, about 1 trillion neutrinos are passing right through your thumb. They're produced in the core of the sun. One of the byproducts of fusion is neutrinos. They stream straight out through the bulk of the sun, and then stream out into space, and some of them are intersecting your body right now. They're completely harmless, but nonetheless, there are trillions of neutrinos passing through your body every second. It doesn't matter if it's day or night. You might think, well, the Earth would block them. It doesn't. They go, if it's nighttime, they come from the sun, they go straight through the Earth and then come up out of the Earth and go through you and harmlessly out into space. Pretty remarkable. Why do they do that? The answer is because atoms are mostly empty space. If I had the nucleus of an atom being kind of the head of a pin, the electron shell would be larger than this room. So atoms are mostly empty space. And so when that neutrino is zipping by, it likely misses one of the two electrons because they have no size anyway and they're zipping around. And then unless it hits that nucleus, which is very unlikely, it's just going to pass right through that atom, right through the next atom, and so on and so forth. So of course, they pass through matter because matter is mostly empty space. In fact, statistically, a neutrino can pass through about 20 trillion miles of solid lead before it is likely to actually impact either the nucleus or one of the electrons. So neutrinos just don't care about any other particles. They just do their own thing. They stream harmlessly through the universe. They're very difficult to detect for that reason. And the only way we can detect them is when they do occasionally hit either the nucleus of an atom or the electron in an atom. So pretty neat. And that might make you wonder, well, why doesn't everything do that? Because why doesn't the electron? I mean, it's got no size as well. Why doesn't it slip through an atom? And the answer is the electron is charged. It's got that negative charge. And so long before it gets to the atom, it can already feel the negative charge of another electron there, and they repel each other. So the reason that electrons, muons, and taus don't pass through matter is they're charged. They are mutually repelled by the electrons in the atom. Now, if you haven't heard about muons or taus, that's because they're not very common, and that's because they disintegrate very quickly. They decay. Many elementary particles are what we call unstable. They will decay, which means they spontaneously change into some other combination of particles. The muon, for example, will decay into an electron and also an electron antineutrino and a muon neutrino. So it produces other particles in the process. Generally, it's the heavier particles that do that. Heavier particles will decay into lighter particles if they can. We also need to know about antileptons then. So the leptons are at the top. These are the symbols that are used for them. So the electron is a lowercase e with a little subscript or superscript of a minus sign. And then the neutrinos are indicated by the Greek letter nu. It looks kind of like a V, it's a nu, with a subscript indicating which species of neutrino, the electron neutrino, the muon, and the tau. And then you have antiparticles. You've heard of antimatter. That's just like matter, but the charges are reversed. They're not as common, but you can have anti-electrons. And I use blue to indicate negative charge, so red indicates positive charge. An anti-electron, also called a positron, it's identical to an electron, except the charge is flipped. So it's positively charged instead of negative. And likewise, you have an anti-muon and you have an anti-tau, and you have 3 antineutrinos. And you might be wondering, how are antineutrinos different from neutrinos since they're both neutral? And the answer is they might not be. In some theories of physics, neutrinos and antineutrinos are identical. In other models of physics, they can be distinguished because one is sort of a mirror reflection of the other, even though the charge is both 0. So there's your antileptons. We're going to find that when particles decay, or when you create new particles from energy, which we can do in particle accelerators, there are certain things that God allows to change and certain things God does not allow to change. The particular flavor of lepton can change. Flavor is what we refer to as the different members of that family. So there's 6 flavors of leptons, 6 flavors of antileptons. God allows them to change. The muon can decay into an electron. But when that happens, there are certain things that God does not allow to change. For example, the total charge can't change. The total energy can't change. There's another conserved property called lepton number. It can't change either. The leptons have each lepton has a lepton number of +1. Antileptons have a lepton number of -1. And what that means is if I take energy and create a new lepton, which we can do from energy, you have to also produce an anti-lepton because the total lepton number has to be 0 before and after. And so there are these conservation rules. I'm not going to go through all these because they get a little bit meaty, but I will point out that mass and energy is always conserved. Therefore, particles can only decay into less massive particles. So a muon can decay, and this is the way a muon decays. So on the left, that's the muon, and on the right is what it decays into. You don't have to do anything, and it decays quickly. It's a fraction of a second. That muon, they have a very limited life. They last a fraction of a second and almost immediately decay into those 3 particles: an electron, muon neutrino, and electron antineutrino. And those, if you add the mass of those 3 particles, it's less than the mass of the muon. You might think, where did the extra mass go? It went into the energy of those neutrinos. So that's one of the rules, is that massive particles can only decay into less massive particles because that conserves mass energy. The total charge has to be conserved. What's the charge before? It's -1. What's the charge afterward? You add up the charge of the 3 particles, it's still -1 because 2 of them are neutral. The total spin state has to be conserved. Muons have a spin of 1/2. Let's say it's spin up, so it'd be +1/2. You add up the spins of the particles after, you see one of them spin down, so it's -1/2. So 1/2 plus 1/2 minus 1/2 is 1/2. And so the total spin state's conserved, and the lepton number's conserved, because the muon has a lepton number of 1. So does the electron and the muon neutrino, but then the antineutrino has a lepton number of -1. My point in this, all this bookkeeping, you can figure out which particles decay, and in many cases, how they would have to decay, just by following these conservation laws. So because these particles obey math, we can predict how they decay in many instances. And so, for example, muons and tau particles are unstable. They are massive, and so they will decay into less massive particles. But the electron is the least massive charged particle, and therefore it cannot decay. Because you might say, well, maybe could it decay into an electron neutrino? That's lighter, yes, but it wouldn't conserve charge. It's got to dump that negative charge, and there's no way to do it because there are no less massive charged particles than an electron. Therefore, it has to be stable. And you can be grateful for that because you've got all kinds of electrons circling the atoms of your body, which makes chemistry right. And so it's very good that electrons don't decay. You can make an atom with muons instead of electrons, but that muon decays very quickly, and one of the particles it decays into is an electron. So the neutrinos are stable, but they have the peculiar ability to oscillate. They can switch from one flavor to another, back and forth. Only neutrinos do that, as far as we know, and antineutrinos. And if you're wondering, how do we know anything about these particles, especially things like muons and taus that last only a fraction of a second and then they're gone? The answer is they can collide particles. They can collide particles together in particle accelerators, and from the energy of that collision, these particles are produced, muons, taus, and they stream away from the collision site and they enter what's called a cloud chamber, and it looks something like that. They leave little trails. There's material in the cloud chamber, and when these particles pass through the cloud chamber, they leave a visible trail. Now, this is almost instantaneous, but we can take a picture of it. And so we can study it later. And physicists will put a magnetic field over that cloud chamber. And when a charged particle is in a magnetic field, it will spiral. And by measuring the size of the spiral, you can determine the mass and the charge of the particle that produced it. So it's pretty amazing. There's more to it than that, but that's partly how physicists figure out these particles that have only a fleeting existence that lasts just a fraction of a second. So we've covered leptons and antileptons. Now we're going to move on to quarks and antiquarks. Quarks are a little bit harder, but on the one hand, they're very similar because they're also, just as there are 6 flavors of leptons, there are 6 flavors of quarks. 3 generations with 2 in each generation. There they are. So, but there are some differences. And the first one that stands out is that quarks have fractional electric charge. Quarks and antiquarks are the only particles, as far as we know, that have a fractional electric charge. The up quark, which is the first one you see there in the upper left, has a charge of +2/3. The down quark just below it has a charge of -1/3. So it's the same type of charge as an electron, but only 1/3 the amount. Very strange. And composite particles don't do that. Composite particles always have an integer charge. It might be 0, but it's always an integer. So they have fractional charge. That's kind of weird. They tend to be a lot heavier than the leptons, with the possible exception of the tau. If you look at the up quark there, I've got the mass listed, and it gets a little complicated with quarks. Usually there are 2 masses listed for a quark using same units. So something weird's going on there, either 2.2 million electron volts or 336 million electron volts. The reason for that is that quarks have kind of an energy field surrounding them. And that energy has mass associated with it. And most of the mass, at least for the lighter generations of quarks, comes from that field. If you could somehow separate the quark from its own field, it wouldn't weigh very much at all. Like the up quark would only be 2.2 MeV. That's called the current mass. But you really can't do that. You can't separate the quark from its field. And so what I think of as the real mass is called the constituent mass. So for an up quark, it's 336 million electron volts. The down quark's just a little heavier, 340 million electron volts. That will turn out to be important later. That's a design feature. The next quark to be discovered was called the strange quark. Again, I love the names. It just makes it easier to remember. The strange quark, a little heavier. Heavier yet is the charm quark. And at that point, physicists had realized that these quarks fit into a natural mathematical progression, and they were able to predict the next 2. The bottom quark, I believe, was predicted, and the top quark was predicted to exist, and they were both subsequently discovered. So again, particles that are predicted to exist on the basis of math, which I think is really cool. The top quark is unbelievably massive. It is the heaviest elementary particle, weighing in at 177 billion electron volts. Very, very massive. And the bottom quark is nothing to be scoffed at. It's 4.7 billion electron volts. So pretty impressive. We're made of primarily the up and down quarks. We'll find that the protons and neutrons are made of those 2 varieties, but the other ones are interesting and they tell us something about physics. The reason that quarks are more complicated than leptons is because quarks always group together with other quarks. You can't study a quark in isolation. And because they always come in these conglomerations, that makes them a little tricky to study. We have to study the particles they make up and then figure out the properties of the quarks from that. So that makes them a little more difficult. You can think of quarks as the extroverts of the universe. They have to be around other quarks. They hate isolation. They have to be around other quarks. There's a reason for that we'll see a little bit later on. Leptons, they don't care. Leptons are introverts. They might hang around with a conglomeration of quarks, like an electron orbiting around a proton, but it kind of keeps its distance. And then you get the neutrinos, which are just downright antisocial. They don't interact with anything, including each other, unless there's a direct collision. So that's the only way you can get a neutrino to talk to you. But the quarks, they stick around other quarks. They always form composite particles. And the interesting thing is, even though the quarks have a fractional charge, the composite particles they form always have an integer charge, which is really weird. I mean, it's really strange. But they'll only group in such a way to produce a particle with a charge of 1 or 2 or -1 or 0, even though the quarks themselves have fractional charge. When quarks group into a larger particle, that particle is called a hadron. So if you've heard of the Large Hadron Collider, they're colliding particles that are made of quarks and bashing them together to see what comes out of that. There are 2 ways primarily in which quarks will group into composite particles. So there are 2 types of hadrons. The first is baryons, and they are made of a combination of exactly 3 quarks, no more, no less. Quarks tend to like to group in groups of 3. Is how they get their name. More on that later. The other way they can do it is you can have 1 quark and an anti-quark. And so you just have 2 of them, but 1 and an anti. And that forms a particle called a meson. So let's start with baryons then, and we'll take a look at those. So baryons, you should like baryons because you're made of them. The protons and neutrons in the nucleus, again, we have a helium atom here depicted. You can see the nucleus there. We zoom in on that. It's got 2 protons always, and usually 2 neutrons in a helium nucleus. The protons are made of 3 quarks. Each proton is made of 3 quarks. Each neutron is made of 3 quarks. And it all works out. If you take a look at which quarks are there, the proton is made of 2 up quarks and 1 down quark. And remember, the up quarks have a charge of plus 2/3. So add that up, plus 2/3, plus 2/3, 4/3. And then the down quark is minus 1/3. It adds up to plus 1. So that's why protons have a charge of plus 1. The neutrons, 2 down quarks, so that'd be minus 1/3, that's minus 2/3. And then the up quark plus 2/3, charge is 0. So neutrons are electrically neutral, even though they're made of particles that are not. It's just the charges cancel out. So that is basically what protons and neutrons would look like if you could kind of see the particles that comprise them. Now, when particles combine this way, their spin states add. And I do have to point out, how quarks can be spin up or spin down. That has nothing to do with the name up quark or down quark. Those are just names. An up quark can either be spin up or spin down. A down quark can be spin up or spin down. It doesn't matter. But it has to be one of the two because they are spin half fermions. So it has to be up or down, spin plus 1/2 or spin minus 1/2. But the spins add. And with protons and neutrons, one of the quarks will always have the opposite spin of the other two. Quarks prefer, when they group together, to have opposite spin states. That's what they like. But when there's 3 of them, 2 of them are going to have the same spin state just by logic. So, so the proton, and we don't know which 2 it'll be. And I've depicted the proton here as having the 2 up quarks with an up spin state and the down quark with a down spin state, but you don't know which it'll be. And in fact, they can swap their spin states, but those add up, plus 1/2, plus 1/2, minus 1/2, those add up to a total spin of 1/2. So protons and neutrons have a spin of 1/2. The spins of their subsequent particles add or subtract if they're in the opposite direction. And likewise with the neutron there. So these 2 particles are part of the baryon family called the nucleon. They're the only 2 members of that family. Nucleons are made of only up and down quarks and have a spin of 1/2. And we should be grateful for them because that's what we're made of. We're made of nucleons. There are 6 families of baryons. These are the lightest 2. The proton is the lightest baryon. The neutron is the second lightest, least massive. One other thing that is, it might be bothering you a little bit is, why do these quarks stick together? Because the up quark, you could see the up quark and the down quark sticking together. They have opposite electric charge. But what keeps the 2 up quarks together? And the fact that they both have, their charge is twice as much. They have 2/3, whereas the down is just negative 1/3. You'd think they'd blow themselves apart. Physicists recognized this early on and realized that there must be another force that is even stronger than the electric force that is somehow binding those quarks together. And we call this the strong force because, again, quantum physicists are not very creative, apparently, with language. And that's fine, or the nuclear strong force sometimes. It is the force that is greater than electromagnetism and keeps those quarks glued together to form that stable baryon. So the other thing that's interesting is if you add up the mass of the up quark, it's 336, another up quark 336, and 340, that comes out as over 1,000. And yet, if you look at the mass on the table there, the proton is 938. What happened to that little extra bit of mass? Well, that binding force between those 3 quarks, that's a negative energy because you'd have to add energy to remove the quarks away from that system because it's an attractive force. And that, because it's so strong, that energy is so much, it manifests as negative mass. It's called mass defect or mass deficit. It reduces the mass of the system a little bit. And so it's often the case that composite particles have less mass than the sum of their constituents, which I think is kind of interesting. So the other thing you might find interesting is the half-life. A lot of baryons are unstable. They will decay into other particles, but the proton won't. The proton has an infinite half-life. It is stable, for which we can be grateful. If it weren't, you would disintegrate with whatever the half-life is of protons, because you're made of lots of protons. The neutron, however, is a little bit unstable. It's got a half-life of 611 seconds. It's about 10 minutes, a little over 10 minutes. And that is really weird for 2 reasons. One, almost all other quantum particles, that if they're going to decay, they decay in the tiniest fraction of a second. Some quantum particles last a few millionths of a billionth of a second, and they're gone. And most of them have a half-life, that's much less than a second. With a neutron, it's like 10 minutes. So it's just kind of a weird half-life for a particle. And then the other thing, you might be concerned about that. Wait a minute, aren't there a lot of neutrons in the atoms of my body? Yes. The oxygen atom, for example, has 8 neutrons and 8 protons. Long story short, when neutrons are bound to protons, that has a stabilizing influence on them. A neutron by itself is unstable. If it's part of a nucleus, that can make it stable. I won't get into the details of that, but I think it's interesting that neutrons by themselves are unstable and their half-life's like 10 minutes. Weird. The reason that neutrons can decay is because they're a little heavier than the proton. In fact, they will decay into a proton, releasing, what would it be, an electron and electron antineutrino as part of the process to conserve charge, energy, lepton number. So it's because the neutron's a little heavier, it can decay into a proton. And the neutron's a little heavier because it has 2 down quarks, and the down quark is just a little heavier than the up quark. If it weren't, if God had made the up quark slightly heavier than the down quark, then the neutron would be lighter than the proton, and the neutron would be stable, and the proton would be unstable and would decay into a neutron. And that would be a problem because the most abundant element in the universe is ordinary hydrogen, which is just a proton with an electron orbiting it, which means ordinary hydrogen, which is 90% of the universe, could not exist for more than about 10 minutes before half of it would have decayed into neutrons. What are stars made of? Hydrogen gas. What's the sun made of? Hydrogen gas. So you couldn't have stars and the sun if God had made the up quark a little heavier than the down quark rather than the reverse. So it's just amazing the thought that God put into this to get these particles to be the way they are. You can have delta particles. These are 3 quarks that have, they're made up of up and down quarks, but they're all spin aligned. And so deltas have a spin of 3 halves. And therefore they're fermions, but a little bit weird. And because they're spin aligned, that's a higher energy state. It gives them a little extra mass. So you have the delta plus plus, which is a +2, charge +2 particle. The delta plus is identical in composition to the proton. The only difference is the proton has one of the quarks anti-aligned with the other 2. With the delta, they're all aligned. And that is a very unstable state. So if you look at the half-life of these things, 3.9 times 10 to the -24 seconds. So again, that's, a 4 millionths of a billionth of a second. They do not last long, and they usually decay into protons and neutrons anyway. There are other families. There are lambda particles where you have the up and the down, and then one of the heavier quarks, like a strange or a charm or a bottom quark. There are 3 other families, and they have many members, so I'm just giving you one illustration of each. These are all unstable. All baryons are unstable except the proton, and maybe the neutron if it's in combination with the proton. And that's because baryon number is conserved. Baryons, when they decay, they can only decay into another baryon. And since massive particles can only decay into lighter ones, and since the proton is the lightest baryon, it cannot decay. Same reason the electron doesn't. And so the particles that you're made of, God made them stable, either stable all by themselves, like the proton and electron, or they're stable because of their proximity to protons, like the neutron. I want to talk a little bit about this strong force that is stronger than the electromagnetic repulsion that exists between those 2, that's holding the 3 quarks together, because it's interesting. With the electric force, there are 2 charges, which we label as positive and negative. Those are the 2 types of electric charge. I mean, you can have 0, but in terms of the actual charge, positive or negative. With the strong force, there are 6 types of charge. That makes it a little harder. But we can't just say positive and negative because there's not 3 positives and 3 negative. So what physicists do is they use colors. They assign a color to each of these particles. And so these are the 6 colors of the strong force, the 6 charges. Now, this has nothing to do with literal color. It's not like they're really these colors. It's just when we talk about the charge associated with the strong force, since there's 6 of them, we refer to them as red, green, blue, anti-red, anti-green, anti-blue. The antis are just the complementary color of the regular red, green, and blue. So those are the 6 charges of the strong force. And it gets a little complicated because, with positive and negative, if they're opposite, they attract. If they're the same, they repel. But what do you do when there's 6 charges? It gets a little harder. I will tell you that like charges repel. So red will repel red. A red quark and a red quark will strongly repel each other. But what about the intermediates? What about red and green and red and anti-red? Red and anti-red will attract, but what about red and green? It turns out that quarks always come in one of these three colors, red, green, and blue. Anti-quarks come in one of the other three, anti-red, anti-green, anti-blue. And so they're limited. They don't have all 6 options. They have three of the 6. And any quark can have any one of those colors. The up quark could be red or green or blue. The down quark could be red or green or blue. When they combine into a baryon, it's always the case that one quark will be red, one will be green, and one will be blue. So if you could see color charge, that's what it would look like for every baryon that exists, regardless of whether the quark is an up quark or a down or a strange or charm or whatever. So there you go, which tells you that that must be attractive, right? The red will attract green, red will attract blue, blue will attract red, blue will attract green, green will attract red, green will attract blue. They're mutually attractive. This has to be the color combination for baryon, because if one of them had the same color, it would blow itself apart. Because if say 2 of the quarks were red, they would repel. And like charges repel very strongly, so it would blow itself apart. So all baryons have one red quark, one green, one blue. The individual quarks can swap their colors, but the combination is always red, green, blue, always. And one of the reasons that we use color to indicate these charges is because the way these charges add is exactly the same way literal visual colors add. Like if I take a red spotlight, a green spotlight, a blue spotlight, and shine them on the same place, I get white or neutral, right? It's the same way when you have a composite particle that has one green quark, one red quark, and one blue quark, the overall color of the particle is white or neutral. So it turns out all composite particles are color neutral. They're all white, all of them. And that's because baryons will only group one red, one green, and one blue. That's the only combination that works for them. So that's called color confinement. And likewise with the anti-colors. I don't think we'll go into too much more on that, but anti-baryons always have anti-red, anti-green, anti-blue. Only that combination. And those also combine to make white. So all composite particles are white or color neutral. And that is why the strong force is limited to within the range of, the quarks within a proton, because this proton over here, although they have colored particles, the overall color is white. So there's no strong force between them if there's any distance between them. So that is why your hand doesn't collapse into your other hand and form a black hole. Even though the strong force is there, all the particles that make up your hand in terms of the composite particles are color neutral. It also explains why quarks are extroverts, because that strong force is incredibly powerful. It is the strongest of the 4 fundamental forces, hence the name. Leptons, they don't have color charge. Electrons, neutrinos, they're white, color neutral. They do not feel the strong force. They go next to a quark, they don't care. They just zip right by it. Quarks, however, and antiquarks do have color charge and therefore feel the strong force. So we've been looking at quarks. Antiquarks are just like quarks, but the charges are reversed. And that means not only the electric charge, but also the color charge, the strong force charge. So a quark can be red, green, or blue. An antiquark has to be anti-red, anti-green, anti-blue. And then the charges are opposite. So an up quark has a charge of plus 2/3. An anti-up, anti-quark has a charge of negative 2/3. So they're just flipped. They're just exactly backwards. And so we've seen how quarks can form into, 3 quarks can form a baryon, or 3 antiquarks can form an antibaryon. That works. And then the other combination is a quark and an antiquark, and that forms a particle called a meson. So mesons are just 2 particles. And it's always the case that it'll be red, anti-red, green, anti-green, or blue, anti-blue. Red and anti-green do not attract. In fact, they repel. So that means mesons are also color neutral. And it has to be one of those color combinations. The lightest mesons are called pions. There's about 10 families of mesons. The lightest is the pion. It was the first discovered. It's made of they're made up of up and down quarks and antiquarks, one of each. So you have the positive pion, which is an up quark and a down antiquark. You have the negative pion on the right. That's a down quark and an up antiquark. And then for the neutral pion, you can have an up and an anti-up, or a down and an anti-down. And they can even flip back and forth between those two states, interestingly. That's the lightest mesons. They're very light, 139 for the positive pion. That's kind of weird, because you'd think, what's 2 quarks? It ought to be 2/3 the mass of a proton, but it's much less than that, because the binding energy is so strong, and that creates a great mass defect. All mesons are bosons, because when you add 2 spin half particles, if they're the same, you get spin 1. If they're opposite, you get spin 0, which means mesons are bosons, even though they're made of particles that are fermions. And that's wild, because that means, bosons, you can all put them in the same quantum state. You can put as many mesons into the same state as you want, despite the fact that they're made of particles that cannot do that. I find that very weird, but kind of mind-blowing. All mesons are unstable. They decay in a tiny fraction of a second. You might think, well, they can't be remotely important to anything because they don't last very long. But it turns out the reason that protons and neutrons stick together is due to mesons. There's energy, color energy, associated with a strong force surrounding a proton. And from that energy can form temporary mesons, which can travel from proton to neutron back and forth, and that creates an attractive force between the two of them. And so without mesons, even though they're temporary and they're constantly being created and destroyed in the atoms of your body, if they weren't there, the nucleus of the atom would fall apart. And so we couldn't exist. The only atoms that could exist would be hydrogen. And so again, chemistry would be impossible. So there's other families of mesons. I won't go into that. I want to get to the bosons now. So the fermions are what you're made of, and the bosons are kind of what glues together what you're made of. 4 of the 5 families of bosons are associated with one of the fundamental forces of nature. You have photons, particles of light. Have you ever wondered how this electron over here that's negatively charged, repelling this electron that's negatively charged, how did they know that they're there? I mean, it's not like they're in direct contact. It's not like he has eyes and he can see that one. How does this electron know about that one? And the answer apparently is that from the energy surrounding these electrons, photons, what are called virtual photons, think of them as a temporary photon, can form and travel from one particle to the other, communicating with it, basically saying, hey, move away a little bit, or come a little bit closer if they're oppositely charged. So kind of weird. So a virtual photon is one that you don't actually see it, but mathematically it seems to be there, and it communicates. It allows charged particles to communicate. Photons have no mass. If you could stop a photon, it has 0 mass. It has no electric charge. It has no color charge. It's just barely there. The only real property it has is spin. So you have this object that has no substance to it, but it's spinning, and that gives it some of the properties that it has. That's what makes the electromagnetic force repulsive between like charged particles. So that's the photon. They're stable. They can't decay into anything because particles can only decay into less massive particles. Can't have less mass than no mass. Therefore, photons are stable. And they are their own antiparticle. Because if you reverse a photon, you get a photon. You reverse the charge, it's a photon. They're their own antiparticle. That's often the case with bosons. Another particle, and this is the only one that hasn't been experimentally detected. It's called the graviton. And basically, we know what properties it would have to have because of the way gravity works. So it's one of those mathematical things. We know what it has to be like, even though we haven't physically detected one yet. In the same way that photons transmit information about electric fields, the graviton is supposed to transmit information about masses, and that causes the planets to orbit the sun. It creates that force of gravity. Gravitons would have to have a mass of 0, otherwise gravity would have limited range. We know it's unlimited. It works on cosmic scales. Gravitons have an electric charge of 0. They have an infinite half-life. They're stable because there's nothing less massive to decay into. And they have a spin of 2, which is interesting. And we know they have to have a spin of 2, again, for mathematical reasons. If they had a spin of 1, like the photon, then like charges would repel. Masses would repel other masses. Gravity would be a repulsive force if gravitons had a spin of 1. So God gave them a spin of 2, and that flips it and makes gravity an attractive force. So because they have a spin of 2, we can have things like planets and stars. If we didn't, those things couldn't exist. Now with the strong force, it gets interesting. The strong force is transmitted by particles called gluons. And while there's only one type of photon, one type of graviton, there's 8 types of gluons. They have no mass. They have a spin of 1, like a photon. No electric charge. They don't decay. They have an infinite half-life. But the weird thing is, even though gluons transmit information about the color charge, they also have color charge and anti-color. Like, you remember how quarks have one of the 3 colors and anti-quarks have one of the 3 anti-colors? Each gluon has a color and an anti-color. And so going from the top left there, you have red anti-blue, red anti-green, green anti-blue, green anti-red. Then you have blue anti-red and blue anti-green. And you might be thinking, well, there ought to be 3 more: red anti-red, green anti-green, blue anti-blue. It turns out that gluons can't exist with their own, with the same anti-color, red and anti-red, by themselves, but they can exist in kind of a mathematical combination with another one. And there's 2 mathematical ways that can happen. So there's 2 other gluons. There's no easy way to illustrate this. I can't think of any way to do it. Just have to take my word for it. There's 2 other gluons that you can't picture. And the way they do it is they'll transmit information saying, the red quark saying, hey, blue quark, come a little bit closer. And that creates that attractive force. But because they have color charge, they also swap the colors of the quarks. Here's how it works. So in the top panel, that's the starting position. You have a baryon with 1 red quark, 1 green, 1 blue. And that red quark is going to send off a gluon to the blue quark saying, come a little bit closer. But the gluon that it emits has color charge. And let's say it's red and anti-blue. So the red, it sucks the red away from the quark, so it's not red anymore. And anti-blue has to counter out the blue, you see. So it turns that quark blue. And then it goes over to the blue quark on the right side, where it is absorbed. The anti-blue cancels out the blue, and then the quark absorbs the red from that gluon. So it swaps their colors. So it's just kind of wild the way that works. We have the weak nuclear force. And the main thing you need to know about it is involved in decay. When particles decay from one type to another, it often involves, not always, but it often involves these 3 particles. These transmit the so-called weak force. There's 3 of them: the W plus, the W minus, which are antiparticles of each other. They're charged. And then you have the Z0, which is its own antiparticle. So, and they're highly massive. They're very, very heavy. You got the W plus and minus at 80 billion electron volts, and then the Z at 91 billion electron volts. And that was a surprise. Physicists thought that all force carriers would be massless. When these were discovered, it indicated that our physics isn't quite right. They had to make an adjustment, and that adjustment predicted another particle called the Higgs boson, which was discovered just a few years ago. The Higgs boson, it doesn't transmit any force, but what it does is it's associated with a field that fills the universe and gives other particles mass, depending on how much they interact with the Higgs field. Particles that don't interact with the Higgs field, like photons, have no mass. Particles that do interact with the Higgs field have mass, and if they interact with it strongly, they have a lot of mass. The Higgs is the second most massive elementary particle, 125 billion electron volts. So only the top quark and anti-quark are heavier. So there it is. And again, so there you have it. We've covered every particle, every elementary particle that exists. Everything else is made up of some combination of those. The particles that give you substance, that give you mass, are the ones on the right. And really, just the 3 particles on the right. You get the up and down quarks that make up protons and neutrons, and the electron. You're made up of those. But then you need the particles on the left-hand side to keep those particles stuck together. So all of them contribute in some way to making the universe the way God created it to be. So we've seen that elementary particles exist in a nested hierarchy, and you have some idea what that is now. We've seen their properties are highly mathematical, whether you followed the details or not. And the properties are just right for chemistry to be possible. So I hope that was somewhat tractable. I've never done a talk on this before. It's fascinating, I think, but it's difficult because quantum mechanics is difficult. But I hope that you get a feel for these particles and why they have the properties that they do. Some of them, like the top quark, I don't know that that's necessary for life. God can be creative. He can make things that don't have a purpose that we know of. But a lot of these other particles have to have the properties that they have for life to be the way it is. And the fact that, for example, God created apparently exactly as many electrons as protons in this universe, that's necessary for life, because if it didn't, then the universe would have a net electric charge, and that's far stronger than gravity. You couldn't have planets. Everything would blow itself apart. So all these things are just right for life. They're intriguing. I hope that sort of 40,000 foot overview of quantum particles makes sense. So I think I'll end there and take any questions that you might have.
Oh boy, do we have questions. Okay. So that was very interesting. I think maybe a few people got lost, but they wouldn't admit it. But for the most part, it was very interesting. So I'm trying to decide where to start with our questions. So you just at the end here mentioned purpose. So given the fact that they have such a fleeting existence, what is their purpose?
That's my question.
Yeah, like the mesons, which last a tiny fraction of a second, and yet they're the glue that keeps neutrons and protons attached to each other. The range of the strong force in itself is probably not sufficient to keep neutrons and protons together. So even though these particles have a fleeting existence, they nonetheless act like glue. They're created in the field from the field energy, and then they're reabsorbed in the field energy. But in the process of doing that, they glue the particles together. They keep them together. And by the way, let me add too, the series that I wrote on the website. I think if you've heard this presentation and then you go read the articles, I think it'll really help. There's something about hearing something, seeing slides, and then reading about it. It really kind of reinforces it. So.
And for people, I think we posted it in the comments. If for people watching on Facebook, maybe not, but we'll make sure that we do that. So okay, next. So you also mentioned that, that they have such a fleeting existence, and you talked about how they disappear so quickly, but how do they start? I think you kind of touched on that, but that's one of the questions. How are they, I think you used the word even born or birthed. How does that happen?
They're produced when enormous amount of energy is provided. One of the ways we can produce them is like in the Large Hadron Collider. We slam together protons, for example. If you slam together two protons, the energy from that is enormous. And from that energy, some of these particles will just be born. They'll be born from that energy. And then they almost immediately cease to exist. And there are energies in the cosmos that are sufficient to do that too. There are certain reactions that take place. Well, in the core of a star, you can produce neutrinos there. Of course, they're stable. But there are some other processes like in quasars where the energy is extremely, extremely high. You can form these temporary particles from the energy, and then they almost immediately disintegrate into something that's more stable.
Terry, I want to interject for just 1 minute. Dr. Jason, this is probably a stupid question, or maybe I'm not following, but when you said that they slam together and they become particles or whatever it was, energy, isn't there a law that says there is no new energy, that there is all in, so it's just something converting into something else?
Yep. The total energy is always conserved. And energy and mass, really the same thing, just measured in different ways. Okay. So particles cannot really come into existence from nothing. They come into existence from energy. And so at least anything other than virtual particles, and even there, they come from the vacuum. So yeah, so when we slam protons together, that has tremendous, these are moving at a substantial fraction of the speed of light. And so the energy when they collide is enormous, and it has to go somewhere because energy can't be destroyed. And so a lot of times it will go into making new particles that will come out of that collision. Particle collision is the way to make new particles. That's the way to do it.
And then what governs the spin? So, because you talk about how some of them spin it in integer. Mm-hmm. Why? Like how, why?
God gave them that property. The bosons, the photon has a spin of 1 because that's God decrees that a photon will have a spin of 1. And it has to have that for the electric force to be repulsive for like charges. If the photon had a spin of 2, then electrons would attract other electrons. You couldn't have atoms, things like that. So their spin determines some of these other properties that they have. But as far as I can tell, the only thing that determines their spin is God. We can't change it. We can't make a photon spin any way other than 1. We can flip it upside down, but and make it spin up or spin down. And likewise, the electrons, they have a spin of a half. If they didn't, if they had a spin of 1 or 0, matter wouldn't be possible. God has simply decreed that these particles will spin at that particular rate, and there's nothing that can change the rate.
That's so amazing. So Christopher, I don't know if it was him or his son, he says, if the spin of an elementary particle cannot be slowed or speed up, but it can change direction, when it changes direction, wouldn't that mean that it would have to slow down and then come to a stop and then to start to spin the opposite direction? Would that violate the P law?
Oh, that's clever. Apparently it's instantaneous. When the particle flips, it's just this way and then it's that way. It takes no time for it to flip. And in the process of flipping, it has to, because the total spin has to be conserved, right? So if it's plus 1/2, it can't just be negative 1/2. It has to give off a particle. One way it'll do that is give off a photon. So for example, an electron, let's say in a hydrogen atom, let's say you have an electron that's in a hydrogen atom. Let's say the proton is spin up, spin plus 1/2, the electron is spin plus 1/2. It would be slightly better for them to be anti-aligned. Remember, particles prefer to be anti-aligned. That's a lower energy state. And so in a hydrogen atom, that electron can flip, but it has to get rid of that positive spin. And so it'll give off a photon, a particle of light. And the energy to flip it from this way to that way in a hydrogen atom is a very specific energy. And so it emits light with a very specific wavelength that's exactly 21 centimeters. And astronomers can detect that frequency of light. And we know that there has to be hydrogen gas there because it's an electron flipping from there to there. So it does so instantly and produces a particle in the process that carries away a little bit of that energy and carries away the spin. I hope that makes sense. But apparently it takes no time to flip one way to the other. It's instantaneous.
Yeah. Okay. So here's a question from Facebook. So what happens to the particles in our body after an animal dies? Do those spins or attractions in the particles simply stop?
No, they continue. Dead bodies and living bodies have the same particles in them. It's just the chemistry is a little different when you're alive. You have things moving, blood's flowing, and things like that. But the particles, they don't know or care whether you're alive or dead. The carbon atoms in your body, they're going to keep doing what they do. It doesn't change the spin state or anything like that. They continue to exist, and it's just the chemical reactions are different when you're alive than they are when you're dead.
Okay. Next, can you explain what an electron gun is? And somebody wants to know, is that what Kirk used on Vulcan?
What an electron gun is? I'm not sure. I've heard that term. I'm not going to. Sorry, I'm not going to get into that.
Okay, pass.
Yeah, we can accelerate electrons, so that might be something along those lines. But using magnetic fields, we can accelerate it.
And it's not how you make photon torpedoes either, right?
Right. Yeah, those are
okay. just checking.
Yeah, those are fairly fictional.
Oh, then one of our young viewers is asking, can any of the particles time travel?
So yes, in a way. It turns out that mathematically, an electron and an anti-electron, mathematically, an anti-electron is just an electron that's going in the opposite direction in time. And you can think of that, it kind of explains why the force between an electron and an anti-electron is attractive. Because the electron wants to repel all other electrons. It's saying go away, right? But when the anti-electron gets that signal, it's reversed in time. And so it says, oh, you mean come here? And likewise, when the anti-electron sends out its signal saying go away, the electron receives it, but it's moving in the opposite direction in time. And because electrons and anti-electrons don't carry information, they don't have a preferred direction in time. But you can think of one as being a time reversed version of the other. And there's really good mathematical basis for that. But you can't use it to transmit useful information. That's the key. The rule seems to be information cannot travel back in time. And if it could, then you'd have grandfather paradoxes where you can have something and not something at the same time in the same sense. It leads to a contradiction.
Okay, that I was going to say, it almost sounded like time travel could be a possibility, but then the principle you just said for the logic, the law of contradiction. So yeah, that makes sense. So.
Okay, next, is the current lowest detection limit for mass equal to the mass of 0.8 electron volt per speed of light squared?
For neutrinos, it is. Yeah, that's we know that neutrinos have a mass that is equal to or less than that limit. We haven't been able to measure below that. The way they do these experiments is really brilliant, and they're looking for the slope of a line, and they're seeing where it intercepts, and that should tell you the energy, the mass energy of the neutrino. But we can't detect it below that level. We know it's small, and we know it's non-zero because of the math. Neutrinos have the ability to change flavors. The electron neutrino can turn into a muon neutrino, can turn into a tau, can turn back into a electron neutrino. And it turns out that the math indicates that if they were massless, they couldn't do that. So the fact that they oscillate, and that's been detected experimentally, indicates that they do have a small amount of mass, but it's beyond our threshold to detect at the moment.
Interesting. Okay. There seems to be a contradiction between string theory and elementary particles. If an elementary particle is a point, how can all elementary particles in string theory be vibrating one-dimensional strings?
Well, they could be, but they're at a scale that is so ridiculously small that we'll never be able to measure it. That's one of the things that makes string theory totally untestable. Is the scale of the strings is tiny, but basically string theory is trying to explain some of why particles have the properties that they have by treating them like vibrating strings, and by changing the vibration, you change the particle. It's clever. It may be right. It may be wrong. Nobody can think of any ways to test it because these strings are so small that they're below. There's a limit on kind of the size that we can detect. And it could be that elementary particles do have a little bit of size, but we can't detect it. All of our experiments have failed to detect any size whatsoever to elementary particles. So it's not necessarily a contradiction. It's just string theory is one way of trying to account for the properties of particles that we don't really understand.
Would you say that the string theorists are kind of looking to avoid God in creation?
Not necessarily. I mean, some of them probably are, but not necessarily.
So it is a creationists do that as well, string theory.
Yeah, we're trying to understand the mechanism by which God assigns these particles their properties. And it could be just fiat decree, God's saying, this particle will have these properties, but there could be an underlying reason for it. That is, God is logical. And so a lot of times we can understand, oh, God did it this way, so because of that and so on. Like the fact that quarks are held together by gluons, that's pretty neat. We're understanding the way in which the universe is held together. And that's not in contradiction to the verse that says in Christ, all things are held together. It's just that we now understand a little bit of the mechanism that God uses. And what an honor that God allows us to understand some of the mechanism by which he uses to hold his universe together. Gravity, strong force, electromagnetic force, they're not replacements for God's power. They are God's power. And the fact that we can write down equations that describe them tells us something about the mind of God, that God is very logical and mathematical in the way he thinks about things. So string theory is one way of explaining how God may control particles, basically. And it's an atheist might try to use it to replace God, but a Christian physicist might believe in string theory or not. We can't test it, but there's nothing inherently atheistic about it.
Thank you.
Mm-hmm.
So let's talk about a little more of theology. So on Facebook, we have a question. The Apostle Paul in Ephesians talks about the heavenly realm. That is apparently where angels and demons operate around us. Do you think that the heavenly realms around us are made up of the same stuff or something entirely different that we can't see or access?
Well, that's interesting. I think it's probably something entirely different. We think of a spirit, God is a spirit, and he doesn't have a location in space because he's omnipresent. He's everywhere, meaning his power is immediately available, but he doesn't require dimensions in which to exist. And so that tells me that that's probably a characteristic of a spirit. A spirit doesn't require dimensions in which to exist. It doesn't have a physical location. And so, and we're interesting because we human beings, we have a physical body and we have a spirit too. And so our physical body and our brain, our mind somehow interfaces between the two in a way that's a little mysterious. I don't pretend to have all the details of that, but I think the spirit is something that's not a property of the physical universe. Certainly God created the spirits within us and angels, which are spirits, but I think they're probably not part of the physical universe. I have a feeling that they're not made up of atoms and quarks and things like that.
Okay. We have a few more. Are you okay?
Mm-hmm.
Okay. All right. So we have a couple of questions on Facebook about dark matter and dark energy. So I think there's some questions about whether or not you or creation scientists in general believe in dark energy and dark matter. And then also what's the connection with quantum particles and that.
Okay. So there's very good evidence that dark matter exists. Dark matter is anything that exhibits a gravitational influence on something, and yet we can't directly detect it. So you might think of like a black hole as dark matter, but the weird thing is we think that a good fraction of the universe, like 90% of the mass in the universe, is this dark matter, and that's rather strange. It's kind of surprising that the most abundant substance in the universe is something we don't know what it is. And it presents a challenge for these quantum physics theories, because according to the standard quantum physics theory, we've discovered all the elementary particles that exist. So there shouldn't be, for example, a seventh quark or a seventh lepton, or a second type of photon, or what have you. We think we've got them all, other than the graviton, which hasn't been empirically detected. And yet, ordinary baryonic matter tends to radiate. It gives off photons, not always in the range that we can see, but a lot in the infrared. I mean, you can or microwaves. You can go outside at night and see microwaves. If you could see microwaves, they'd be there. So dark matter doesn't seem to give off any photons, which makes many physicists think it's non-baryonic, that it's not made of quarks. It's something, and that's hard for anyone to understand. How could it, because it's got to be something that we don't know about. It could be a state of quark matter that we haven't discovered yet, like quark nuggets. There's a theory that quarks can form in enormous masses of quarks, where there's just thousands of them compressed into a small space. And these have not been discovered. If they are, it's called a quark nugget. That could explain dark matter, perhaps, because it wouldn't radiate the way normal matter does. So, but there's good evidence that dark matter exists, because we can measure the mass of things in space by seeing how stars orbit in their galaxy, by seeing how light is bent by the gravity of the galaxy. That tells us the amount of mass that's there. And then we add up the amount of mass we can see, and it's like 10% of the amount of mass that we know is there. So dark matter, there's good evidence it exists. We don't know what it is. It could mean that there's more to particle physics than the 38 particles that we know of. It could be there's something else that hasn't been discovered. Dark energy is a little more theoretical, but I think that there's evidence for that as well. There's some evidence that dark energy basically means that empty space has a little bit of mass to it. And therefore it will exhibit a gravitational, it's a little bit perplexing, but it kind of accelerates the expansion of the universe. And there is evidence that that's happening, but not as much as dark matter. I think dark matter is on very good empirical grounds, and dark energy is a little more theoretical, but there is evidence for it.
So there's a comment here to follow up before we move to our next question on Facebook. Somebody says, I love that secular scientists say there's no God, but over 90% of the universe we can't study or understand. That's because true. It doesn't respond to light, and we need light to study anything. Yeah. God's mind is not limited by our minds.
That's a good point.
That's a good point. Okay, so another question, how would you respond to those who say that realist interpretations of quantum mechanics are ruled out by measurement experiments?
Well, I'd have to pin that down a little bit to see what they really mean by that, because quantum physics, it really happens. And there's good evidence that these things occur. There are some weird implications of quantum mechanics. There's what's called the Copenhagen interpretation, where a particle, until you observe it, it acts like a wave, and a particle can have decayed and not have decayed at the same time until you observe it. But I can reject that interpretation and still do the math of quantum mechanics. There's nothing inherently illogical or unrealism in terms of quantum mechanics itself. Some of the interpretations people put on top of it, like the Copenhagen interpretation, are a little bit, I think, absurd in the way that they're often stated. I think they violate the law of non-contradiction. But I can throw away that interpretation and still do the math. And let's put it this way. The model that we have in terms of the way we think about particles and their properties, we can make incredibly successful specific predictions about what will happen, about the spectra of light based on the electron levels and so on. And so it's a very useful model. Is it perfect? Probably not. There's probably improvements to be made. That's not surprising, but I don't think there's anything that's inherently anti-real about the model. I think it works pretty well in terms of obeying laws of logic and things like that. I'm not sure if that answers the question, but that's the best I can do.
I think it's good. One more follow-up to the string theory question. Are the strings in string theory smaller than the Planck length?
They may be. I'm not sure. They may be, in which case we could never measure them, because that's kind of the limit on what you can do. So I'm not sure, but I suspect probably so. And that's one reason why we can't really find any way to test it.
Okay, this is the last question, and it comes from Facebook at RMCF. So I don't know if you know what that.
Rocky Mountain Creation Fellowship, maybe. Maybe
so. A speaker a decade or more ago talked about his ideas of atomic particles as spinning energy rings, not particles. Any comments of what you understood that to be about? Any validity to it still, or application to this particle physics?
Yeah, I don't think that works. When I first heard about that, I thought, well, that's kind of intriguing. And I'm always open to, new ways of understanding things, but it doesn't make successful predictions that quantum mechanics does. So yeah, I don't think that's right. I think that guy passed away actually, and he was a Christian. I have no doubt about that, but I think he's wrong about that. So quantum mechanics, I'm not saying that it's right in every aspect, but I will tell you it makes correct predictions about the results of experimental phenomena. And it's again, the math behind this, we've been able to predict new particles that are then discovered. So that tells me that we're really on the right track. We've got a pretty good model here. It may need refinement. I think everybody thinks it needs some refinement, but we have to be on the right track if we're predicting which particles exist and then finding them. I think that's pretty impressive. I haven't seen any alternative that can do that.
Okay, well, that's gonna wrap up our time online. So as far as our live stream for Facebook and the recording. So before we go off, and then I think there's a couple of people who wanna hang back and ask you one or two more questions, if you don't mind, in Zoom. So, but before we sign off, can you please tell everybody where they can find you and support your ministry and buy your products, because they're all worthwhile purchase.
Yes, thank you for that. So we're at the Biblical Science Institute, and we're on the web, biblicalscienceinstitute.com. That's the way to find us. We'll have a web store on that site. You can go there and get our resources there. There are lots of free articles on the website, including a series on quantum particles. And so I like to say, I know I talk a little too fast, but I wrote the articles really slowly, so you can take your time with them and really enjoy that, let that sink in. So anyway, in fact, we have a new resource that'll come out just in a matter of days it's actually a series of Sunday school classes that I led on logic, and that'll be out on DVD within a matter of days. So check back on our website for that. And you can support us there too. We have a partner donation tab if you want to support us. We're funded by donations primarily, and book sales to some extent, but yeah, we certainly would appreciate that, and it allows us to keep doing more of these things and writing more books that confirm that creation is true, that God's word is true from the beginning.
And I'll remind everybody that about 1.5 years ago, you came on with us and you did an overview of your Introduction to Logic course. So on our list of videos, people can find that if they're interested in before they invest more, they can learn a little more, and then they'll realize they should invest more. And And several of us have noticed that there's been a big increase in your social media activity. I was telling your assistant Denise the other day, I can barely ever open my phone without seeing something. So I know Leilani is here tonight, so we want to give a shout out to her, and she wants to make sure that we remind everybody about your Facebook pages, Jason Lisle and Biblical Science Institute. So, and also a couple of people have commented on the Facebook stream about the James Webb Space Telescope. And I just said, we don't really have time to talk about that, but you did write an article, 2 articles, one that predicted what your predictions were, and then one after the fact. So we want to encourage people to look at that as well. And the video that you did with Dr. Faulkner and was it Rob Webb, I think, from Answers in Genesis. So those were good resources. So
maybe Dr. Lisle would like to come back in 2023 and talk about the James Webb Telescope, whatever it is.
I can do that. I'd be happy to do that.
All right, we'll book that. Denise? Okay. All right. And then, of course, we are Creation Fellowship Santee, and you can find most links to most of our past presentations by typing in tinyurl.com/CF Santee. So C for creation, F for fellowship, and Santee is spelled Santee. You can also email us at creationfellowshipsantee@gmail.com so you don't miss any of our upcoming speakers. And with that, we're going to thank you, Dr. Lisle, and we're going to go ahead and sign off the live stream.